21.
21, okay. So we're looking at 21 on the review. So this is my best approximation to the graph that you have on your paper, but it's probably not going to be perfect. So I know it's really hard to read. This thing over here, this mark right here on your the actual graph on your reviews is supposed to say x sub 0, and I know that's not very clear at all. Still on the x-axis over here is marked 1, and so we know x sub 0 and 1 on the x. So this is telling us where that place is. This is giving us a scale factor now, so we have an idea of what 1 on the x looks like. And please notice the scale on the y is very different. So on the y, this point, let me back up a little bit here. So this point on the y is marked as y sub 1. And then this is, I believe, 1 on the y-axis. So this is 1 on the y, whereas this is 1 on the x. So very different scaling, and that's going to be important. So I'm going to erase all this stuff for a minute there. Okay, and I'm going to, we're doing this before class, so I'm going to get to where we are here. So we know that, and I used F's, but these are really given as P's. And so this is the P of X is our curve right there. So what we want to know, we're trying to rank these in order from smallest to largest. So all these are numbers, but some of these numbers come from the X coordinates of points on the curve, and some of these are going to come from Y coordinates of points on the curve. And so this is trying to make you really think about, where does the input value come from, where does the output value come from, and make sure you're clear on that. And then into the mix, we have these very different scalings on the X and Y, so you have to be very careful about how you kind of assess how big these numbers are. So these are numbers, and we're going to try to get them from left to right. So we're going to kind of sort this through and kind of go through where these come from and try to put some kind of note to how big they are. So when we look at x sub 0, we know that y sub 0 is p of x sub 0. And so, well, and here's x sub 0 right there. So I guess we're okay on that. Now you can see it's positive because it's right of the y-axis. But you can also see, since 1 on the x is way over here, this is a very small positive number. So I'm just going to make a note to myself now before we figure out what the actual ordering of this is. But that's going to be a small positive number. Okay, that's the x sub 0. Now the y sub 0 is the y coordinate of the point on the curve whose x value is x sub 0. So we're going to come down to the curve and we're going to read across here. And this y value then must be what y sub 0 is. Now notice, because on the y this is 1, we're negative because we're below the x-axis, but this is like, I don't know, -4, -5, something like that. I'm going to call that in our scheme here a large negative number compared to like this x sub 0 that's a small positive because it's less than 1. So this is the y sub 0. How did I skip over that? So large negative there, and this x sub 1. So let's find x sub 1. Well, we know that y sub 1 is equal to p of x sub 1. This, we're told, is y sub 1. So the x value that generates, that goes with that point right here, that's going to be our x sub 1. And we can see it's left of the y-axis, so it's negative. Well, remember, the scaling on the x is way different than y. If that's 1, then right over here is going to be -1. So this is a negative number that's in between 0 and -1. I'm going to call that a small negative, since it's less than, in between 0 and -1. So the x sub 1 here is going to be a small negative number, and we know what 0 is. Now y sub 1 is the y value, well, we have it right here, it's the y value that goes with that point. So we come across here, and it's above the x-axis, so it's positive, but because of the scaling here, this is bigger than 1. And so I'm going to call that a large positive number. Does that make sense? So now we can go back and say, okay, now we can go from smallest to largest. Well, the negatives are smaller than 0 and the positives. And a large negative is going to be smaller than a small negative. I know that seems weird. Okay, but like -5 is going to be less than -1. So the smallest one is going to be that y sub 0. And then we're going to get the small negative comes next. That's the x sub 1. 0 is next. And then we have a small positive x sub 0 and a large positive, and that's y sub 1. And so that's going to be our ordering on that one. Make sense? So let's try another problem like that. Now, I'm going to try to make up a new one here. I don't know, what do you think? Can we work with this one? Or should I redesign that? People that were trying this before class. Could you change that?
Redo it.
Redo it?
Those two numbers that were
Too close? Okay. So I'm going to try to make up a different one here. Now I'm going to use my graph here, which I'm sure is not exactly the same as what you have on your paper. So let's go off of this one here. So I'm going to try to make this up here and see if we can rank these. So let's say we're going to rank P of 1, include 0 in the mix. We will do P of 0. We'll do the negative of P of x sub 0. And we'll do P of -1. That gives us 5 values there. So see if you can figure out how to rank those in order from smallest to largest. And discussion and conversation is encouraged. Okay? I'll give you a minute to digest that. I think we need an AP calculus problem. You might want to be thinking, making notes to yourself, you know, is it positive, is it negative, is it a big positive, is it a small negative, you know, give some kind of note to yourself to start the ranking process there. And then we can talk about it. Katrina, did you guys ever get to this one or no?
No.
Okay, you may steal that one then. Feel free to talk to somebody about this. Compare your answers.
So since one is the part, also, Mr. Street,
Yes.
can I come in lunch and do test questions?
Not lunch, I do before school, after school.
Can I come in after school day?
Yes, that would be great. We ready to start talking? Or do you need another minute?
I mean, I'm good. You guys good?
Should we start talking then? Okay, so let's see what we know. P of 1. So here's 1. P of 1 is going to be this y value. So I'm going to mark it right there is our P of 1. And so that's going to be, in our scheme, since that's 1, that's, I don't know, somewhere in the neighborhood of -2, something like that. Does that sound reasonable? So I'm going to say about -2 just as a note to myself. Is that okay? 0 we know. P of 0 is going to be where? Compared to P of 1, is it going to be above or below?
Below.
Yeah, so it's going to be right here. Right there's P of 1, right there, P of 0. Okay, so it's going to be, I'm going to say -3, just to give myself some scaling, that this is below that one. Negative P of x of 0. So we have to find P of x of 0 first. So here's x of 0, come down here. This y sub 0 is the same as P of x of 0. Then we take the negative of that, so that's going to reflect it and put it up here. So up here is going to be our negative P of x of 0. So I don't know, that's 1, 2, 3, I'm going to say maybe roughly 4, something like that. So approximately a positive 4. And now P of -1. So here's 1. P of -1 means we have to go over, somewhere over there is going to be -1. And then P of that means we're going to go way up there. So this is like off the charts big, right? So that we say mathematically is huge. Okay. Question? Make sense? Okay, so then we can rank them. So the smallest is going to be
Negative.
P of 0.
yeah, P of 0, because a -3 is smaller than -2, right? I think number line left is smaller than right. So P of 0 is going to be the smallest. P of 1 will be the next, 0, and then the negative P of x of 0 and the P of -1 is the biggest. How's that feel? Better? You want to try another one, or should we move on? Test, test. Is this on?
I think we're good.
We're good? Okay, so I'm going to do the next
I
one.
think silence is a concern.
Silence means we're okay. I'm not seeing tears being shed, so then that's my cue to move on. Okay,
Only my calculus, or only my chemistry notes are tears today.
so I think we, at least this morning, there was a question on how to graph one of those crazy ones there. So, of course, that's off camera. So you can see what it is right here. See if you can come up with a graph for this. And then I'm going to transfer that over where we can see it on this side of the board. And I'm going to add in here that it is a continuous function. Okay, so we are going to try to graph a continuous function. Let's say a continuous function that satisfies these other things. A continuous function with the following properties. Okay, so one is that it's going to be increasing on the interval from -2 to 0. And it's going to be decreasing. Yeah. It's going to be decreasing on the intervals from -infinity to -2, and also from 0 to infinity. It's going to be concave down on the intervals from -infinity to -2, and from -2 to 1. Now, let me just make a comment here. Remember that that concavity is always an open interval. So the fact that it is concave down on the interval from -2 to 1 does not mean that the function doesn't exist at -2 or at 1, because in fact it's a continuous function, which means there aren't going to be any gaps. There's no holes in the graph there. That's just the way we talk about concavity. Concavity never includes endpoints, even though the function is defined at those endpoints. Okay, that's a common mistake I see in the past. It's going to be concave up on the interval from 1 to infinity. It's going to have a horizontal asymptote, which I'm going to abbreviate as HA, a horizontal asymptote at y equals 0. And we're going to know that I'm going to give you a few anchor points here. So I would start by plotting these points. So we know that f of 0 is equal to 2. We know that f of -2 is equal to -2. And we know that f of 1 is equal to 1. So I would start the graph by plotting these points, and then building from there, how are you going to move from one interval to the next. And I would do a number line and mark where it's going to be increasing and concave up, where it's going to be decreasing, concave down, and so on. Increasing here. It's going to be decreasing here. And it's going to be decreasing also here. It's going to be concave up. So I need 1 in there. There's 1. It's going to be concave up here. It's going to be concave down here. And also there. I forgot I got a horizontal asymptote at y equals 0. And remember, a horizontal asymptote, it just has to approach that in one direction. Doesn't have to be both directions. I believe, as I made this up, I intended. Maybe I'll tell you, it's going to be, I'll say it's to the right. I don't think it is, if I remember how I made this one up. But it's actually a horizontal asymptote to the left. That's maybe a bit much to ask going in. Oh, I think I did that wrong. Well, I don't know if I can make that work now. What do you think? We ready or need another? Not ready yet.
I'm sorry, I was making, oh, you're fine.
Yeah, so.
I got that.
But the thing is, it can't cross this.
But like it goes down. I think that if it's a horizontal, it's going to the right. I think, but there's an asymptote. Does it cross? Yeah, but it can only do it on one side.
Oh, I didn't know.
Because it's a continuous function.
Nice. I didn't know.
Also, I don't think you should have like two lines with the asymptote. Because like.
That's okay.
I know.
Is that why we do it?
That's true.
No, I mean like when you're line continuous in the bottom, so.
So it's gonna be kind of a funky looking graph there.
Wait, where did we?
Has some weird features.
Like this or like this?
I think it would just be a that.
How did you do it? Did you like that or like that? I did it like this.
I guess you could use that to do that.
Wait, hold on. It's
I don't know.
from negative
I
to
think the
zero.
vertex would be at the y-intercept because,
Sorry, if it goes from.
Well, no, that's it, but for this one, did you just use like a
Oh,
bounce?
yeah, that's what I did.
Well, why am I so Mr. Street has to say?
Are we ready to talk?
If I'm wrong or not.
Kobe, you ready to talk? Okay, so let's go piece by piece here. So we're going to be decreasing and concave down up until we get to x equals -2. So I want decreasing, concave down. So I'm going to do something like that. And I guess I could have included the asymptote going this way as well. I didn't intend it that way. So here's one version of that would work. An alternative version we could have, I thought that through. We could have still made it approach that asymptote to the left as well. That might have actually been kind of cooler, but that's okay. Now, from -2 to 0, now we switch to increasing, but it's still concave down. So how does that look here if it's going to go to increasing, but now be still concave down?
And it looks like it.
It's going to have to come to some kind of a point there. Yeah, something we might call, in calculus, we might call it a corner or a cusp, where it's not nice and smooth. It's going to have some kind of point to it. And we're going to now increase and be concave down all the way until we get to 0, 2. Okay? So that's one kind of curious feature about this is it's got this kind of pointy part of the graph there, not a nice gentle curve to it. Then from 0 to, for the rest of the way, we're going to be decreasing, but we're still in that part where it is concave down. So we're decreasing and concave down until we get to 1. So that means this is going to be a nice gentle bend over here as opposed to the sharp point over there. Now here at 1, it's going to continue to decrease, but now it's changing concavity. So this is what we would call an inflection point. So it's still going down, and then it's got to approach this asymptote. So now it's going to gently kind of try to approach a landing over there, although it doesn't necessarily ever have to actually land. So a couple features here. A horizontal asymptote is a guide to what happens at the very end of the graph. It is not like the Berlin Wall or something that cannot be crossed. So a horizontal asymptote you can cross. What this means is as we go further out, the curve gets closer and closer to that line. But what happens in the middle of the graph, anything goes.
On the test, will you specify like horizontal asymptote to the right?
Yes.
Okay.
Okay.
I can remember my rights and left.
You know right and left. Now, vertical asymptote we couldn't cross. Okay, that can't happen. So if you have a curve with a vertical asymptote, it's going to be in 2 separate pieces. There'll be a piece on one side and a separate piece on the other that are not connected. But that doesn't have to happen with a horizontal asymptote. So it would be possible to, I mean, the other information doesn't support that because it's decreasing and concave up. That's the only way to draw this. But in general, you could have a horizontal asymptote where the curve crosses crossed it and then approached from the other side, that would still be an asymptote. You could, crazily enough, have something where it's just got to get closer and closer to that y-axis. So it could start by crossing it an infinite number of times, but those kind of peaks and valleys are getting smaller and smaller and smaller. That will still qualify as a horizontal asymptote because the curve, that purple curve, is getting closer to that horizontal line as you go further out. So those are all ways that you could see a horizontal asymptote. Okay, good. All right. Other questions from the review? Would you like to see clarified or an extra practice problem?
Number 24.
24. So 24, it says let f and g be two invertible functions. What in the world does that mean? What does invertible mean? It's the top comes off. No, that's a convertible. Invertible is what? They have inverses that are functions, such that f inverse of x is, and is that the cube root of x plus 1?
Yes.
And we know that g of x is equal to 3x minus 4. So we want to find f of g of inverse of negative 10. Ooh, goodness.
So we need to find it.
No, you don't. It's easier than that. So what we have is this. Let's see, if this we know about g, so you could find the inverse functions and do it all that way. That's not the intention of the problem. So the intention was to do it a little bit more efficiently and think about this. So if we want g inverse first of negative 10, that's an input value for inverse of 10, which is the same as an output value for g. You with me there? So what we could do is go to g and set that equal to negative 10. Now just solve this fairly simple equation and find out what that x value is. That x value for g will be what g inverse has as an output value. Does that make sense? So I don't have to do find the whole g inverse. So then we can add the 4, I think that makes that a negative 6, and so x is negative 2. So when negative 2, negative 10 is an ordered pair for g, then negative 10, negative 2 is an ordered pair for the inverse. So that tells us the output value for g inverse is going to be, in this case, a negative 2. Does that make sense? Now, same story. Now, f of 2, well, we don't have f, we have f inverse. But an input value for f will be an output value for the inverse. With me? ID. Okay, so I can set that equal to negative 2 and now solve that. So we can cube both sides and get x plus 1 equals negative 2 cubed is negative 8. Subtract the 1, and that's going to be negative 9. And that is our answer, without actually having to find the inverses of each of those functions. That was the intent of the problem. Other questions?
Nineteen.
19. So, in the graph on this, so we're trying to do this whole translation thing from the graph. And this is another one that's tough to read. So I'm going to try to plot these important points. And I would think of these as endpoints and corner points rather than think of it as going on forever. I think it's going to be easier to keep track of. So that first upper left endpoint is at what? 1, 2, 3, 4, negative 5, 3. Does that sound right? 1, 2, 3, 4, negative 5, 1, 2, 3. And we'll let that be right here. And I'm going to make that negative 5, 3. Is that point? Because then when I do this translation, I'm just going to look at these key points and see what happens to them. That corner point down here looks like it's at negative 3, negative 1. Does that sound right?
Yeah.
I'm going to call that -3, -1. And then the point right on the y-axis at -1 is going to be 0, -1. And the other point looks like it's at 3, 3. So 1, 2, 3, and that's going to be 3, 3. Okay, so here is the graph that we are given. And then we are going to try to graph f of x minus 3 minus 1. So what we know from this is that each of those key points, the corner points and the end points, are going to get moved right 3 and down 1. And so that's what we're going to do. We're going to go from here, right 3, 1, 2, 3, and down 1 is going to put us right there. And that's going to be at -2, 2. Is that okay? And then this point, 1, 2, 3, and down, 1, 2, 3, and down 1 is going to put us at 0, -2. And this point, we're going to 1, 2, 3, and down 1. That's going to be at 3, -2. And this point, 1, 2, 3, and down 1 is going to put us at 6, 2. And then we can connect those important corner points, and that's how the whole figure is going to get translated, right 3 and down 1. Anything else? So if you want more practice, find it after school today if you can. There's also, I believe, there is a video, I think, in the support materials where there are some problems worked out. I don't know what these particular ones are. That might give you some more practice problems as well. Okay, let me go find my brains here. So we're going to start talking about quadratics today. So hopefully this is a review, but we'll try to treat it like we're sort of seeing it for the first time. So we will see 3 different forms of a quadratic equation. So we will see 3 versions of a quadratic equation. And we'll just start talking about one of them today, but in the next few days we'll talk about the others. So the first version is going to be, I guess, what we would call standard form. And that's going to be y equals ax squared plus bx plus c. And so you can see here kind of what makes a quadratic is that it has an x squared in it. The highest power of x that you see is going to be 2. And then we don't have any fractional exponents or negative exponents or anything like that. Now b and c could be 0. So y equals x squared is a quadratic. But you could get something non-zero as well. A can't be 0 or it's not quadratic. It's linear. The second form we're going to talk about is vertex form. Not today, eventually. And that's the y minus k equals a times x minus h squared. Or some people write it more as they have gotten the y by itself and put the k on the other side. I'm okay with either one. It doesn't matter to me. So this is nice because you can see the vertex is right there at h and k. And the third form that we will look at is the factored form. And so that's where we have this factored y is equal to a times, and I'll say x minus r times x minus s. So the r and s are going to be the x-intercepts of that parabola. So I'll say r0 and s0 are the x-intercepts. So that's going to tell us where that parabola crosses the x-axis. So we will at various times be given these to start with and then try to figure out the graph, or we'll try to put it into one of those forms given a different form. And I'm going to start with this one right here. So in all cases, we're looking at trying to graph these most of the time. Sometimes we'll do other well, but we will be interested. So we will be interested in finding the vertex, which is oftentimes very challenging, not so much when you have vertex form. We will in general be looking for a y-intercept, which in general is not too difficult to find. That's kind of a nice point. That's low-hanging fruit. We will find what we're going to call the symmetric point. So that is the point that is from the symmetry of the parabola that is on the other side of the vertex from the y-intercept. So once you know the vertex and the y-intercept, that's fairly easy to find, and then it gives you a nice shape to your parabola. No worry about it, we'll talk about it here shortly. Not everybody does that. We'll, in general, try to find the x-intercepts where they exist. So I will say x-intercepts. And that, in general, can be very challenging as well. So we'll be trying to factor, or if not, use quadratic formula. We'll talk about the axis of symmetry. That is going to be that vertical line, axis of symmetry, that contains the vertex, kind of splits that parabola in half, and then in most of the cases we'll be trying to come up with a graph. Okay? So what we're going to do today is we're going to use standard form, and we're going to find a couple of different ways of finding the vertex depending on what we know and find it. But I'm going to show you one particular way of finding the vertex today, and then we'll talk about finding the x-intercepts and see when it works nice and when it doesn't, what we have to do. Okay, so we are going to start with y equals x squared minus 4x minus 5. And we're going to find all of those things there. Okay, so we're going to find the vertex, the y-intercept. I'm going to leave that there for a moment and come up with the graph. Now, there's a couple ways you can find the vertex. So we're going to talk about method 1 today. The method we're going to save till later is the completing the square, putting it into vertex form. So the other way, the one that is kind of a go-to for me personally, but you can make your decision there, is that we will know that the x-coordinate of the vertex is negative b over 2a. Now, if you are a math teacher, this is quite memorable, and I don't have a hard time myself remembering that, even when I haven't done it for a year. But not everybody is a math teacher, not everybody remembers that, and it's kind of useless if you don't remember how to start, how to get the vertex this way. But let me show you kind of where it comes from. So if you remember the quadratic formula, which of course you must remember this. So the hope is you do know and remember the quadratic formula. If not, you know, this is one of those things you must remember even as you get very old and senile and you forget the names of your kids. You still say, well, of course, the quadratic formula is, and maybe you have to hum it if that's the way you learned it the first time, as I know some of you may have. So remind me how it starts again, this whole quadratic formula thing.
X equals negative b, also minus the square, b squared minus 4ac, all over.
Okay. There's the Papa Goes the Weasel people who've learned that, so clearly you have.
Oh my gosh. Yeah.
So this you must remember. So now if you think about what this means, this holds the key to this right here. So if I split this apart, that is negative b over 2a, right? Plus or minus the square root of b squared minus 4ac all over 2a. So what that's saying is that if you are graphing a parabola, and if this is a real number, so if b squared minus 4ac is a positive number, then its square root exists, and we're going to get that the two places where this is 0, okay, the two places that make our parabola equal to 0 are going to be negative b over 2a plus whatever this is, and negative b over 2a minus whatever that is. You with me there? So I'm going to just arbitrarily say there's negative b over 2a, and so one x-intercept is going to be negative b over 2a plus this. I don't know what that is, but I'm going to say it's that distance over here is the negative b over 2a plus that, then negative b over 2a minus that must be the same distance on the other side. That's going to be over there. So if those are the two x-intercepts, whether our parabola opens up or whether it opens down, that vertex has to lie on that line that goes through negative b over 2a. That means the vertex must have x-coordinate negative b over 2a. That's where that comes from. So my point being that for this method to be effective, you have to remember that it starts with negative b over 2a. If that's hard, think back, hum a little bit your quadratic formula, and you will see there is the negative b over 2a that you need to find the vertex. Does that kind of make sense? Okay, so it's not magic. So our vertex is going to be, well, what is in this case negative b over 2a. So the negative b over 2a is going to be, well, what's negative b? 4. And what's 2a?
2.
And 4 divided by 2 is 2. So there's the x-coordinate of our vertex. And the y-coordinate comes from just plugging in the 2. So 2 squared is going to be 4. Negative 4 times 2 is a minus 8 minus 5. So that's going to be negative 9. So we have that our graph is going to have vertex at 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 9. And is this parabola going to open up or down?
Up.
So I can safely put the 2, negative 9 down below and not run my parabola into it. We okay with that? Now earlier, and I meant to say that, we know from hopefully your Algebra 2 days that when you have an equation in the form y equals ax squared plus bx plus c, the a is what drives the whole shape of that parabola. If a is negative, it's going to open down. If a is positive, it opens up. If a is 1, it's going to be that kind of shape of our parent function y equals x squared. The rest of this stuff is just going to move it so the vertex may end up in a different place. If the a is bigger than 1, it's going to be stretched vertically, which means it's going to be skinnier. And if a is less than 1, it's going to be shrunk vertically, which is going to make it be wider. So it's going to be how narrow or wide it is depends entirely on the a. That's the same a that we saw in the other forms of our parabola as well. So there is the vertex. That's usually, that and the x-intercepts are usually the hardest. So the y-intercept we find, so to find the y-intercept, what do we do in all cases? No matter what kind of equation we have, parabola or otherwise, to find a y-intercept,
Plug in 0.
we plug in 0 for the x. And so generally that's pretty pain-free. So you can just look at that and tell them the y-intercept is going to be negative 5. So we're going to go to 0, negative 5, 1, 2, 3, 4, 5. That's going to be right there, and I'm going to label that. Now, what we mean by the symmetric point is you can see now how this parabola is taking shape. Vertex is down here, we've got a y-intercept, we know it's opening up. So from the symmetry of the parabola, there is another point over here that is the same distance from the vertex but on the other side and the same height. Right? It's got the same y-coordinate and it's going to be the same horizontal distance on the other side of the vertex. That's what we're calling the symmetric point. What would its coordinates be in this case?
4, negative 5.
Exactly. So 4, negative 5. That's our symmetric point. Okay? And then to find the x-intercepts, we're going to set that equal to 0 and solve. So in this carefully constructed problem, this is just going to be a mere factoring problem. If it doesn't factor, then the unfortunate news is you're going to have to use that quadratic formula and figure out where to place it on the graph. This is not so bad. I'll give you a moment to come up with that. So you do your box and diamond if you're a box and diamond person. Guess and check if you know how to do that. Anybody got it yet? Or are you just waiting for me to get it? What a great strategy.
It doesn't factor.
You want to review the box diamond thing? Do you remember that?
No.
Okay, so the diamond thing, remember, you're going to multiply those together, and that's going to be a negative 5x squared. You take the middle term here. Now you want two things that multiply to be the negative 5x squared and add to be the negative 4x.
No, negative 5x.
It doesn't matter which one you put in, negative 5x and x. Then you go to your box, remember? And in one of the diagonals, it doesn't matter which diagonal, you're going to put the squared term, x squared, and the last term, negative 5. Okay, either, I don't know how you've learned it, one of those diagonals. Then these two numbers you came up with, the x and the negative 5x, go in the other diagonal, whichever one you want. Now looking at that top row, what's the greatest common factor?
X.
And then looking above it, what do you multiply that x by to get that x squared?
X.
Okay, now we're in a row. So x times what is going to be this x? 1, and in fact a positive 1. X times what's going to be the negative 5x?
Negative 5.
That's the negative 5. And just to confirm, the negative 5 times 1 does give you the negative 5. So it's going to factor into x plus 1, x minus 5. So x is going to be 5 and negative 1. So our intercepts are going to be 5, 0, and negative 1, 0. And now with 5 points, we should get a pretty accurate parabola out of that. And then the axis of symmetry is that vertical line that contains the vertex. And remember, just as we want to label points with ordered pairs, like the intercepts, an equation of a line needs an equal sign too. So this is going to be x equals that 2. All right, well, I did not get to here. We're going to have to review some factoring here. And so you may need to look at that support materials. There's a video there that walks through some of that because I don't think we're going to get all the way through it today. But things like factoring by grouping, greatest common factor, and then just brushing up also on quadratic formula and how do you factor something when the leading coefficient isn't 1. Okay, and I'll try to put some more support materials up there too before the weekend. Okay, questions on what's going on tomorrow or Friday? Yeah, tomorrow. Friday is already tomorrow. So we got. So just show up at 8 again in the cafeteria.
I'm just gonna stay here.
And I'll be here before that. Oh, you guys got practice in the
Yeah, we
morning?
have some practice,
Okay,
so we'll
yeah.
probably just hang out there.
That's fine. Bring something to eat so you got some fuel.
What time is
Bring
it?
it all out.
You're gonna-